Very good evening to one and all. Let's start the session today. It won't be live streamed immediately, but we'll put it in the YouTube channel later. Due to some technical error, we are not getting that GUI. That's the reason today we took a little 10 minutes time for that solving the resolution of that problem. Sorry for that delay. First and foremost, I would like to welcome Dr. Akshata Shenoy.
Thank you,
On
sir.
behalf of KSTA, on behalf of all the teachers and students who have joined with us today in this WebEx platform, on behalf of all of us, welcome ma'am once again. Also, I would like to welcome all the teaching faculty and students who have joined with us in this session. Welcome you all. So today, Dr. Akshata ma'am will be speaking on quantum physics. Before starting this today's session, I would like to give a brief introduction about Dr. Akshata ma'am. She has done her PhD from Indian Institute of Science, Bangalore, and she is the recipient of Swiss Government Excellence Postdoctoral Fellowship for pursuing her postdoctoral studies in quantum cryptography at the University of Geneva in Switzerland. Furthermore, she has also conducted postdoctoral research at the University of Bangalore, India, and the International Center for Theory of Quantum Technologies, which is known as ICTQT, University of Gdansk in Poland. Currently, she is a senior researcher at the center and working on topics related to quantum cryptography, quantum correlations, and applications of machine learning. He is also collaborating with industry to benchmark various aspects of quantum technologies. With this brief introduction, I welcome Dr. Akshata ma'am to deliver a session on realistic applications of basic quantum phenomena, quantum bomb detection scheme. Over to you, ma'am. Thank you.
Thank you, sir. Thank you, KSTA, for giving me this nice opportunity to speak to a young audience, is what I am told. So I'm just going to share my screen and probably stop the video because I have a lot of pictures in my slides. I think my video might block them. So here are my slides. I hope my screen is visible now.
Yes, ma'am. Yes,
Okay.
ma'am.
Okay, thank you. Yes, and here is my pointer. Okay, great. So don't be confused with the title of my talk. I'm not going to talk about some military applications and things like this. I'm going to talk about really some fundamental concepts of physics or quantum information, to be specific, but from a point of view of applications, because I come from an application end, and that is how I look at fundamentals of physics. So as Umesh sir said, I'm a researcher at ICTQT in Gdansk. So where are we based? We are based here in the north of Poland, and these are some nice pictures of the old town in Gdansk. And ICTQT is a theory department. I think this is one of the largest theory departments in Poland. It is based in University of Gdansk. So just to tell you the contents of my talk today, I'm going to focus on some basic concepts which you might have heard somewhere in some video when reading something, and you don't understand them and would like to know more. And then I'm going to focus on non-locality, or rather non-classical aspect of quantum physics, and manifestation of these features, some applications in between as and when I describe these concepts. And I'm also told by KST and Umesh sir to like touch upon certain career options in this area, which I will do so. And I will also be adding some skill set which you might require to actually carry studies in this area. So initially, let's look at some basic properties of quantum particles. Okay, classical bits can have only two states. We know that, like they can either be in a state 0 or 1. But qubit, which is a quantum bit, can be in a uniform superposition of 0 and 1. Here these alpha and beta are probability amplitudes and their mod squared sums to 1. Okay, so the total probability should always sum to 1. Another important feature of quantum particles is the no cloning theorem. You know that in classical physics or in general, if you, let's say you have a paper and you want to make photocopies of this, so you can easily do it by a photocopier machine and you don't care about what are the contents of this paper. But within quantum mechanics, an unknown state, quantum state, cannot be cloned. This is prohibited. A classical object, when it is measured, it retains its states. Okay, so you can measure its position, you can make measurement of different properties of it. The classical object is not going to get disturbed or changed, but measurement of a quantum system disturbs the state. This one we can actually ignore for the time being. The uncertainty principle, I think most of you have already heard of this in the form of Heisenberg uncertainty principle, where we say that one cannot measure the position and momentum of a particle simultaneously, that you cannot measure two properties of a quantum particle simultaneously with arbitrary accuracy. Quantum entanglement, these are pairs or groups of particles which do not have individual description. Okay, for the time being, let's ignore this. I'm going to tell you more about it in the later part of my talk. So first, let us see why quantum particles are different from their classical counterparts. What do you mean by non-locality or non-classical behavior of quantum particles? Imagine that you have a football in a location A and another football in a far off location B. Okay, now you are kicking this football in this location A, playing with it, or in general doing some operations on it. You know for sure whatever you do to this football in location A, it is not going to affect the football in location B because it is in a very far off place. The only objects which are going to be affected, let's say by you kicking the ball, maybe some other objects which are in the vicinity of this ball in location A. Okay, unless and until some objects are close to the football in this location A, it is not going to affect it. But quantum mechanics allows for objects which are in a certain location to affect objects which are in a very far off location. Okay, for example, quantum mechanics allows for objects in location A and B, and you making some operation on location A might have an effect on the object in location B. So this is what is called as quantum entanglement, and this effect almost seems to be instantaneous. Okay, this is an intriguing feature of quantum mechanics. So we are going to look at two resources within quantum mechanics. One is quantum entanglement, where you have two particles, okay, and they are connected to each other in some strange manner, that if you put one particle in location A and in the other one in the location B, doing something on one of them affects the other one in the other location. And then in the second part of my talk, we are going to look at non-classicality of single particles. And here, this is just a picture of a source. It could be a laser source, and then there are some other optical components like non-linear crystal and something which can be used to produce entanglement. Okay, two photons. So Einstein was very concerned about non-locality. He called this affecting or operation on one part of the one part here, that I mean by location A, and its effect on the part B as spooky action at a distance. Okay, so in their famous paper, Einstein, Podolsky, and Rosen, which is famously known as the EPR paradox, in 1935, they have discussed this in quite detail. So what worried Einstein mostly was that is our understanding of nature via quantum mechanics a complete description of it. How is it possible that you make some operations at a location and this affects in a non-local way some other object which is far away? So Einstein always thought that there should be something which is not accessible to us, and that is why we don't understand this non-local effect. Because the idea was that for a theory, physical theory, to be successful, it has to be correct and it has to be complete. So according to him, or this is what he understood, that quantum theory was complete and what you saw is what you saw, but sorry, quantum theory was correct. You observed this phenomena of entanglement, but was it complete? So he believed that there was some hidden description of this non-local effect which is to be understood, and then we need to find an explanation of this. Okay, so please remember this, that his worry was this exact, this sentence which I have given here, that is our understanding of quantum nature via quantum mechanics a complete description of reality. Now in his letter to Bohr, this is what Einstein writes. I have just taken a small part of it, and this here is just an article from a newspaper back then. So let me read what Einstein writes to Bohr. He writes that quantum mechanics is impressive, but an inner voice tells me that it is not the real thing. The theory produces a good deal. That is, okay, it is exhibiting some very intriguing features, but hardly brings us closer to the secret of the older one. That is, he says that we are not able to understand it in terms of what we already know in physics. So I am at all events convinced that he does not play dice. By he here he means God. So this is his famous statement, which I think most of you might have already heard, that God does not play dice. So this is in context with the incompleteness of quantum theory. Now, in 1964, John Bell, he was aware of EPR paradox and all the discussion happening with respect to completeness of quantum theory. So what did he do was that he tried to devise this inequality here, which is famously known as the Bell inequality. And what were the implications of this, and how could one understand quantum theory from this perspective, is what he aimed at. For example, he made two assumptions. One is the realism, the other one is non-locality. So what does realism say is that objects have definite properties, whether or not someone is looking at it or not. Okay, for example, you know that you have classical objects, like you have a table, chair, desk, and you have other macroscopic objects. So whether you measure them, whether you don't measure them, they're still going to remain the same. Their properties, like their color, their size, their shape, everything is going to remain the same. So this is his first assumption. The second assumption is locality. Operations on one object should not influence another object if they are spatially apart from each other. So this is what exactly we know, that if there are two objects which are spatially separated, like one in location A and in another in location B, they are two distinct objects. You do something in location A, it should not affect another object in a far off place. Okay, they are two distinct objects. So this is what classical mechanics tells us. So he makes these two assumptions, and then he devises this experiment where he says that, okay, we have, let's say, Alice in some location A and Bob in another location B. So now they are supposed to test for this inequality. Okay, so Alice has a device and she is allowed to make two measurements, A0 and A1, and these small A0 and A1 are the outcomes of this capital A0 and A1. Similarly, Bob is allowed to make two measurements, B0 and B1, and the corresponding outcome of this is small b0 and b1. Okay, and now note that these a zeros, both the capital ones and the small ones, they can only take +1 or -1 value. Okay, they, of course, they, let's in the physical sense, it just means that I could be making some measurement, like some x measurement or a z measurement. I don't want to get into the details, but just think that, okay, these settings or outcomes as we call it, they can take two values, +1 or -1. Now what you could do is that take this inequality and try to substitute in this inequality. Okay, just manually make a column A0, B0, A1, B1 and substitute, for example, +1, -1, iterate to all the possible values and then check for this inequality. You're always going to see that this will be less than or equal to 2. Okay, so the idea is that if you have a classical resource, that if you have some classical objects shared between Alice and Bob, and then they make some measurements A0, A1 by Alice and B0, B1 by Bob respectively, never are they going to exceed this value or violate this inequality. They cannot do better than 2. Okay, but imagine that now Alice and Bob are sharing a quantum system like an entangled system or quantum entanglement, as I showed you before. Then all these measurements implemented on this quantum state shared between Alice and Bob, this is going to violate this inequality. That is, a quantum state shared between Alice and Bob is always going to violate this inequality maximally in the case of certain states known as Bell states, like you're going to get 2 root 2. So this is a violation of the inequality. So here John Bell demonstrated that quantum mechanics is very, very different from classical mechanics. Yes, quantum mechanics is correct. It is incomplete, but like Einstein suggested or pointed out that can we have complete this theory by having a classical description or some hidden variable description which may not be immediately accessible to us? This is not possible. So the physical implementation of this experiment is that you can never have a classical description, a classical view, or a hidden variable description of quantum phenomena. Okay, please note that Bell is now not talking about completeness of the theory. No, he's not completing the theory. He's just ruling out the possibility of completing the theory via hidden variable models or classical models. Okay, this is a very subtle point, so please don't be confused with it. Now, uh, yeah, so the word quantum entanglement, I think you might have heard this in various contexts. I see that now a lot of sitcoms are also referring to it. I think the famous one among them is the Big Bang Theory, where I think Sheldon Cooper is always talking about quantum entanglement in different contexts. So the word was coined by Erwin Schrödinger, where he says that quantum entanglement is a characteristic of quantum mechanics, the one that enforces its entire departure from classical thoughts. He means that quantum entanglement is very characteristic or iconic of quantum mechanics, and which is something that cannot be attributed to classical physics. Okay, and for people who are interested, there is something known as the Schrodinger cat thought experiment, where you can check whether a cat is dead or alive. I encourage you to look up this thought experiment. It's quite interesting. This is actually my cat. I just wanted to like show you here that entangled states can be one of the entangled. This is an example of one of the entangled state. They can be written like this, where 0 indicates whether the cat is dead and 1 indicates whether the cat is alive. And whether the cat is dead or alive, this is actually in a superposition, and you can only you cannot distinguish them, that you cannot talk about this state or this state of particle A or B separately. Okay, you have to always talk about them together as a composite system and not as individual systems. So what does John Bell have to say about quantum correlations? Is that it's a correlation that is stronger than any classical correlation. And for Asher Perez, who is another famous physicist, he thought that it was like magical. It was a magical phenomena that could not be imitated by classical magicians. Now here on the left side, I think for you, this is how an entangled photon or an entangled system is generated in a laboratory environment. Here this is a non-linear crystal, and the pump is a highly coherent laser beam which is illuminated on this non-linear crystal. Of course, there are certain conditions to be satisfied. I think this is not for the current audience. And upon like these conditions being satisfied, it is possible for you to generate two entangled down converted photons. Okay, so they can be entangled, for example, in polarization. If one is in vertical, the other can be in horizontal, just like here. If one is in horizontal, the other one could be vertical. Okay. Uh, all right. So just to emphasize how important like quantum entanglement uh, is for applications in quantum information, I would like to like point out the Nobel Prize in Physics in 2022, which was given to three eminent physicists, Alian Aspe, John Clauser, and Anton Zeilinger, for their experiments with entangled photons and also for experiments with Bell inequalities, the inequality that I showed you here. This is just the theoretical part, but in practice, this was quite hard to implement. Even now, I think if you have to close something called as the loopholes, okay, the complexity of the experiment itself is quite involved. And yeah, so for violation of Bell inequalities and for other pioneering applications, for example, Anton Zeilinger here, he has not only worked on the foundational part but also on the application side of quantum information. And yes, this is a nice introduction of the laureates and why they have been uh, given this Nobel Prize. This is from the Nobel web page. So this is a nice illustration of entanglement, that there are two particles and maybe there is some kind of connection between them. Maybe we don't see it. We don't know how they are correlated. Okay. Yeah. So this is what it reads, that okay, these three physicists have done like immense work and they have laid the foundation for era of quantum technology by demonstrating that how two objects separated far apart, really far apart. Okay, there are some experiments where you can see that these two photons were on different like islands. One photon was one island and the other one was in another island, and then how they could still demonstrate entanglement or Bell inequalities. So please do look up, there are like a lot of material on the internet. Okay, and in the context of our institute, I would just like to tell you that at ICTQT, there are like some eminent physicists who have contributed immensely to understanding entanglement theory, especially the Horodetsky family, where Richard Horodetsky is the father of like Pavel, Michał, and Karol, and they have all been working in like quantum information since quite some time and have really made like very I think strong contributions to quantum entanglement theory, and then applications for cryptography, thermodynamics, and they're still like active. They work here at the institute. And Professor Marek Zukowski, who is our current director at ICTQT, he is actually worked in close collaboration with Professor Anton Zeilinger, the Nobel laureate that I showed you in the earlier slide. And it is his work along with Professor Zukowski which has like contributed to the Nobel Prize. I think Professor Zukowski is even the prime author of most of these papers. And here is another like eminent physicist, Professor Harald Wienfurter. He is in actually Germany, but he's also associated with our institute, and he's an experimentalist and has worked extensively on Bell inequalities and entanglement experiments. Now, former paradoxes of quantum foundations are resources of quantum information science. What do I mean by that? Like entanglement was seen something as a paradox which was not understood. It is still, I think, not understood to a larger extent in terms of the basic phenomena itself. But then, how can we apply it to applications? What can we do with entanglement? So you can see that entanglement has found immense application in communication and cryptography. Especially, I think the most popular one is establishment of quantum internet. These are like global network nodes which could be established all over the earth, okay, if they are terrestrial nodes. And at each node you can have quantum devices which can transmit quantum signals, receive quantum signals, process them, and you can run quantum cryptographic protocols. Please don't be confused that like in the future, okay, maybe all your classical communication is going to be replaced by quantum communication. No, I think both of them are going to run side by side. So what would be expected in the future are hybrid networks where let's say you will have both quantum and classical devices working at node A, B, C, everywhere, and then they would be running classical and quantum protocols. And these yellow lines, these could be your fiber optic cables, just like your classical communication. Okay. The other way where one could achieve quantum internet, because look, optical fibers, they are land based, and sometimes it is difficult to scale distances, okay, especially with respect to like quantum systems, because they're very fragile and very susceptible to noise. But if you want to scale larger distances and cover like more locations on the earth, the best option would be for you to go for satellite communication, where you have these four configurations. uh, One is the downlink, where you have the source which is on the satellite. The satellite keeps moving around the earth, and when it is at a location above the earth where you have this receiver, it will beam down light, and then yes, you can establish some communication. Similarly, for the uplink, where the source is on the ground station and the photo detector is placed on the satellite, and this is a configuration for entanglement distribution. I'll next give you an example where the Chinese physicist team have distributed entanglement between 2 points and Earth at a distance of like 1,200 kilometers. So it has been done actually in practice. This is another configuration where you can have two sources, which are two sources and two photo detectors, okay, where two satellites are sending and receiving signals between each other, and they can also simultaneously establish communication with the ground based nodes. So the best, I think, quantum internet solution would be for you to have this terrestrial network and also the space network working in tandem together, okay, so that you are able to reach out to almost all the locations on Earth, let's say. Now, examples of experiments at space scale. Uh, Please look up. There are like some amazing examples of this. Now, these examples are from the Chinese team, where they use the satellite Mischius, named after the Chinese philosopher, to establish communication. You can see like various examples. One is the entanglement distribution and bell test. They have also done quantum key distribution between China and Vienna, which was then the key, which was developed using quantum physics, was then used in a classical protocol to establish video conferencing between Chinese Academy of Sciences and Austrian Academy of Sciences. And yes, so these are some more examples of the uplink and the downlink cases. And for a detailed like explanation of what are the experiments planned under this quest scheme, please look up. I think there is a lot of material again on this. Now let us come to the second part of my talk. So far, we have seen non-locality or non-classicality from the perspective of two body objects. Okay, that there is quantum entanglement. It consists of two particles, A and B, and you separate them, and they will affect each other non-locally when you make operations on them. So this is one form of non-classicality. Now, the other form of non-classicality we are going to look at are from the perspective of single systems. Okay, even single systems or single photon, for you to understand physically, they also exhibit some form of non-classicality. They can also have some non-classical effects via what you know as quantum superposition. So we are going to understand this better from an experiment known as the quantum bomb detection scheme, okay, which can be used to detect a quantum bomb or an object which might be in a certain place, and you want to do it without interacting it. Okay, for example, imagine that there is a mine or a quantum bomb which is placed in a certain location. Now you want to detect whether this is present or there without triggering the bomb itself, because this bomb is now light sensitive, so you don't want to disturb it. It may be very fragile, and if you want to measure it, interact with it, and then detect it, it might just trigger the bomb. Okay. Yes, so this is a very nice paper which proposed this scheme known as the quantum mechanical interaction free measurements by Elidzor and Weidman. This is available on archive and it is easily downloadable for students. If you are interested, please do take a look. It's written in a very nice manner and it's easy to understand. You can ignore the math if you're not comfortable with it, but you will still get the gist and the essence of what they want to say in the paper. So what is the aim of the current experiment is that we are going to describe a type of a measurement which, when successful, will determine the existence of an object in a certain location without us interacting or directly touching or making measurements on this object. This is known as quantum interaction free measurement, and it has no classical analog. To understand better, in some sense, this experiment exhibits like wave particle duality. I don't want to like get into the details, but just want to highlight this point because I know that most of you are familiar with Young's double slit experiment for wave particle duality, which is at the heart of quantum mechanics. So this is another experiment, I think, which is also at the heart of quantum mechanics, which exhibits quantum non-locality or non-classicality in a very nice way. So let me give you two examples of interaction free measurement. This one is a classical one and this one is a quantum one. Imagine that now you are told, okay, you are told that there is an object now in one of the boxes, either box A or box B. Now you have to infer in which of the boxes is this object, for a ball, for example, and these boxes are like completely sealed, okay, and this object which is placed inside the box gives you no signatures of its existence, okay, no signatures. For example, maybe it doesn't give any electromagnetic field which you can measure and then detects its presence, nothing, absolutely nothing. And now you have to ascertain in which of these boxes is the object in a without interacting with it directly or making measurements. Suppose you open the box A and look inside this box. And you know now that, okay, you have looked inside this box and you don't find this ball inside this box. And you know for sure now that the ball is present in the box B. Okay. Now this is an example of interaction free measurement. You have looked in box A, you have opened the box, you have not found the object there. For sure, now you know that the object is in box B. But remember that somebody has definitely told you that definitely that the object is in this box. There is this assumption that you know for sure that this object, this ball, has been placed in one of the boxes. Suppose now you had looked into this box A and had found the object or the ball in this box. Now you have looked or touched or measured this box A and you have found the object there. This is not an interaction free measurement, okay? If you looked and you found the object there, this is not an example of interaction free measurement. You looked at it and interacted with it directly. But if you looked into the box and found the object elsewhere, then you didn't interact with it, but you are able to ascertain that it is present there. Okay. So this is an example of interaction free measurement. This is what I mean by it. Now, we have already looked at quantum entanglement so far. So, and we know that even if they are two particles which are entangled, if they are separated like in two far off distance locations, some kind of quantum correlations exist between them, and you do something to one, you know what happens to the other. So, doing something at location A on a particle A will tell you something about particle B. So this is also another form of interaction free measurement where you get to know about particle B without doing something to it directly, but this works out because they share some kind of quantum correlation between them. Now let us look at the same thing from a perspective of a single photon, okay, or a single quantum system. But is it possible to do the same without having prior knowledge of it? For example, see that in the earlier case, somebody told us, okay, there is this object which is present in a certain location, but we don't know exactly where. So you have to find out where is this object located exactly by interaction free measurement. But now suppose we have to ascertain the presence of this object in a certain location but without having the knowledge whether this object is present there or not. Okay, so we do not have any information whether an object is present in a certain location. We have to do some experiments or some interaction free measurements and then determine whether this object exists in this place or no. Okay, this is an Maxenter interferometer. I am not sure if the students are familiar with this. If you're not, it's fine, but just think of it as an experimental setup which we are going to use to detect the presence of this object. Here, this is a source which generates single photons. So continuously there are single photons which are coming out of this and it hits a beam splitter, BS1. This is a 50-50 beam splitter for this particular experiment. That means that if you have a single photon which is hitting your beam splitter, then there is 50% probability that it is reflected and 50% probability that it is transmitted. Okay, M1 and M2 are mirrors, we just reflect whatever is hitting them. And then you have another beam splitter BS2, which is also a 50-50 beam splitter. And then you have two detectors here, D1 and D2. They are photodetectors. So now if you have a setup like this and there is a continuous train of photons which is hitting your beam splitter, you can arrange this experimental setup in such a manner that no photons are detected at D2, which is known as destructive interference, and all the photons are detected at detector D1. Okay, this is the constructive interference or the constructive port. Now, standard proper math exists for this. We will not go into the details, but for sure you can look it up. And I can also tell you that for the quantum bomb detection scheme, there are many examples, videos, and also there are some nice codes like Python codes on the internet. You can download them, try to run them, and then experiment with this setup. Okay, so what we understand is that when we have this kind of an experimental setup, always you are going to have a detection at D1 and never at D2. Now, suppose there is an object which is placed in one of the arms, say arm B of the interferometer, but you're not aware of it. Okay, nobody is going to tell you that, okay, the object has been placed. The objects may have been placed, it may have not been placed, it may exist there or not exist there. But now it is your job, or it is the aim of your experiment, to find out whether an object, a bomb, quantum bomb, or a mine has now been placed in one of the arms. So here are the three possibilities if there is an obstruction or a mine in one of the interferometer arms. Okay, the first one is that you may observe no detection at all with probability half. Again, this can be calculated. You can find it in the paper that I gave you, by the paper by Elitzer and Bedman. So why is it that there are some events where you do not observe detector clicks? This might have happened because the photons might have traveled to this mine itself and might have been absorbed by it or triggered this bomb or triggered this mine, and then it might not have reached this detector D1 or D2. Okay. Another possibility is that you observe D1 detection with 1/4 probability. Now look, in the earlier case, when you did not have any obstruction, you know that always you get D1 detection when photons are traveling to the interferometer. And never you get D2 detector because it's a destructive port. Now, if you observe a D1 detection in this case, you cannot be sure whether it came from this case when there was no obstruction or in this case when there was an obstruction. Okay, so we do not have any information of whether the bomb exists in one of the arms or no. Now let us suppose you observe a D2 detection. Now for sure we know that there is an obstruction or a bomb or a mine in one of the arms. Why? Suppose a photon has hit this beam splitter, and if it had taken this path, then the probability of no detector click also exists because it would have just triggered the bomb. It would have interacted with it here. Okay. For sure, if you observe a D2 detector, you know that the photon might have taken this path and then got detected hit here. This is one possibility. And you also know that the D2 is a dark port. You can never have detection in D2 port if you do not have any obstruction in this interferometer. So if you observe a D2 detector, you know for sure that the interferometer has some obstruction or some mine or some bomb. So the presence of this bomb in one of the arms is now detected with probability 1/4 by clicking of the detector D2. So what are the implications of this? This just shows that a photon, even though it is a single particle, somehow, even by taking this route, it has been able to detect the presence of an object in the other arm. This comes because of quantum superposition. The photon exists in a superposition of these two arms, arm in A and arm B. Okay, so this is in some sense a non-classical behavior of the photon. There are, I think the implications are much more deeper, and for I think it's not suitable right now for this audience. But if you really want to understand much more, please, I recommend you to go through the paper. Yeah, this is just something for fun. There is something called as a quantum minesweeper game which can be found online. And if you want to understand the bomb detection scheme in a fun manner, then I totally recommend this. So here you can see these are like the probabilities. So here it's 3.1, and when I click this, I know that there is like a bomb. So can you avoid these mines or bombs? For example, here you see it was 4.6, so I did not click the next areas because I know that the probability of finding the bomb there is very high. Just so try it out for fun and for maybe understanding the experiment in a better manner. Now, one of the practical implementation applications of the quantum bomb detection scheme is for the counterfactual quantum cryptography, where the presence of an object here at Bob can be sensed by these detector D1 and D2, just like I told you here. So the D2 detection here can give you something called as a key, okay, ones or it's zeros, and then that can be used for as a random key for secret communication. Okay, so now I come to the last part. Actually, KST it told me to give you some career options or possible career in quantum information. So there are many options. Like I think the most of the jobs now are coming up in machine learning, software engineering, hardware, and algorithm, and many more. But there are different routes to take. I would say that it's not to have a career in quantum information. It's not always necessary for you to have done your masters or a PhD or um, any such course with specific to quantum information. It's possible for you to do like quantum information or even computation from different routes. That by that I mean you can have a master's in let's say computer science or mathematics. You can be an engineer and you could still do quantum information because it's a very specific and specialized branch of physics, and you can approach it via different routes. It's a very interdisciplinary and a diverse area. That's the reason why you can approach it by different routes. So if you are looking to do masters, I would still recommend you to do a masters in physics rather than in quantum information, because quantum information can still be learned at a later stage. There are master's program in quantum information abroad. I think in India also I think there is an MTech course in ISC, but still people are looking to introduce such courses in India is what I hear. In abroad, such courses exist. There is one course in our institute also, which is quite intensive, but I would still suggest that a master's in physics is something which I have done and which I think is like the best possible route to approach this, by also talking to other students here who are doing this master's course. And I also get these questions generally from students. They are very interested to come abroad to do a master's course. In my opinion, and in the opinion of some of the students who are here and students whom I have spoken to before, I think we have very good master's courses in India. So I'm not discouraging you to come abroad for masters, but if you are looking for a master's course, then I think really it's a very nice thing to do it in India, because we have really very good courses in physics. And then probably maybe if you want to move for your PhD or some other job like an algorithm scientist or something, then probably you may look to move abroad or even continue in India. The thing why I emphasize you to do your masters in India is that because there are now a lot of students who are coming abroad to do masters. One thing is that it's very, very expensive to do a master's abroad. You have to fund yourself. You do not have fellowships. So I see that many of the Indian students come here and then they are struggling. They are also sometimes taking a part-time jobs to support themselves. Sometimes I feel it's really not worth it. So if you are really interested in doing a master's abroad, I don't discourage you to do it, but please consult your parents, think about your financial status, and do you really want to come for a master's course abroad. If you are still interested in coming abroad, then I would strongly suggest you to come for a PhD, because then your PhD is fully funded. You get scholarships just like you get in India, and this is fine. You can support yourself without being dependent on your family. And yeah, this is something which I think is most important for students. And normally people are focusing on career options, but they forget that you have to develop certain skills to be able to do something. Now, irrespective of whether you want to do quantum information or you want to do any other subject, be it math, be it physics, chemistry, I would suggest each one of you to learn coding, because nowadays I think, be it science, be it any kind of jobs in the industry, uh, even in the industry, you have scientific jobs and you have like completely tech development jobs. I think you have to know coding. It is becoming more and more applied now and numerical in nature. So coding is really going to help you. For example, you could learn probably Python or C++, and then it doesn't matter. You can adapt to either doing machine learning, I don't know, software engineering, whatever you want. But please develop strong coding skills. Mm, and then oral and writing. I see that uh, most of the students whom I interact with do have good oral skills, but writing is something that people don't like to do. Focus on writing in a very elegant manner. Try to convey what you want to say, be it scientific or even when you're writing exams, in a very precise manner by, nice choice of words. So good writing and oral skills is something which is very, very important, irrespective of like whatever you choose as your career option. And then try to develop general awareness, because I see that nowadays there is lot of material, lot of information, and with AI, students trying to use chat gpt, they are exposed to like lot of things, but try to filter out what is like necessary for you, what is truth, that is another thing, what is genuine and what is not genuine. This is also very important. And then critical thinking, try to develop critical thinking, try to analyze what is happening and is this genuine, for example, or how do you approach a problem. And in general, be curious and do not stop learning, always enjoy learning. And if you are interested in learning quantum information or computation, there is lot of learning material on the web. And if you're looking for something specific, you can always write to me. I'm not so hard to find. You can find my email ID on ICTQT webpage, and then please approach me, and then I can point out if you are interested in certain specific things. And in the context of quantum computing, I would also like to point out, like, there is a nice NPTEL lecture by IIT Bombay, which is very, very nice. I think he dev also like explains the math behind these things quite well. I totally recommend that. Okay, so with this, I would like to thank you for your attention. And if you have any questions, I would then like to take them now. Okay, I think I see some question here in the chat box. So where does the root of this quantum theory come from? Okay. So this is coming from actually observing such phenomena like entanglement and then superposition, and also like wave particle duality. So certain experiments were made, for example, or certain phenomena was observed, like in the case of entanglement, and then people try to explain or find an explanation of this in terms of whatever was already known in physics, for example, classical mechanics. And then we still don't have the answer. We still don't know, like, how to complete quantum theory. It's not a complete theory. We know that, okay, we cannot have an explanation of it in terms of classical physics. Okay, so that is the root. Anything relevant to ancient Vedas of India with respect to quantum theory? Mm, I don't know directly with respect to quantum theory, but there are some things called as time traveling, which also like comes within the framework of some studies with respect to quantum theory. And there are some people here like with the ICTQT who work on this. And in Bharata, I know that there are some very strong references to time travel. Okay, so I think time travel and also parts of like quantum theory was known in India. So now the time travel with respect to Mahabharata, I think this is with Revati and her father traveling from some other universe to meet uh, Krishna and Balarama. So, and then when they reach Earth, I know that because of time traveling, their height and everything is different. And then, yeah, they have to be shrunk, okay, and they have to be brought to our time zone. So, I think there are some references, but I don't know how exactly with respect to entanglement and all, or what I have spoken, but definitely there are. Why is it termed as a bomb? Oh, it's just the way the authors write it, that if you have a bomb, it is very, very sensitive. It is so sensitive that that even one photon, if it interacts with the bomb, no, it is going to trigger it. All right. So can you use some subtle features of quantum physics to not disturb this bomb and still detect it? Okay, it's not a robust bomb. It's a very light sensitive bomb. So yeah, it's just what the authors used. And then yeah, this is a very interesting way of, I think, telling it to the students. You can like Google this quantum bomb detector scheme. You are even going to find some nice codes to run it. How do you relate this with respect to intensity of the laser beam? We are using single photons, so it's just one photon. But if you want to do the same experiment with, let's say you have a strong laser beam in your laboratory, you want to do the same experiment, then you have to attenuate it. Okay, so the intensity has to be made very, very, very weak. That at an instant you are going, this pulse should have on an average one photon, something like this. So very weak laser beam also can be used to do this experiment. How can they be implemented in the industry for product development? Yes, they can be implemented. I showed you this mine game or the quantum mine sweeper. This is how exactly, I mean, I don't know it how much, look, experimentally it's possible to do it, but in a practical scenario I don't know how feasible it is, because look, it also depends on the development of such a device to detect it. But once we have these devices, maybe it's even possible to do it. Kindly let us know about the application related to the same three. I believe that this is more feasible for the. It's hard for yes. I'm not sure if it's hard for engineers, but it was aimed for physicists because I think the theme given to me by KSTA was physics. Not to schedule any talks at this point of the
So
resolution.
the last two questions are only for us.
Ah, okay.
Some few of the teaching faculty who are engineering stream,
Ah,
they have joined, so they have mentioned it as their feedback. Not
okay, okay. Yeah, but I would still like to say, like, even if you are an engineer, there is a branch of quantum engineering which is now has come to prominence because most of the work now is being done in engineering. Okay, so I am sure you're, as engineers, you are interested in applications, but please remember you still have to know the phenomena behind it. Whether you approach the applications from foundations to applications or application to foundations, it doesn't matter. But now it's all about physics. Applications are more physics oriented, so you cannot escape it. I understand it is hard for you, but still there is no escape. I mean, physics has to be done
yes, ma'am.
at some point. Okay. I had seen a review article more descriptive. You have mentioned bomb sensing.
Professor K.S. Mallesh sir has joined and he has
Ah,
the
yes, I
question. Yes, ma'am.
see it. So I would like to answer him. Yeah, there are actually, sir, many articles on these bomb detection schemes. There are like modified versions of it in terms of interpretation, in terms of application. But yes, the Elizabeth Medun one does contain mad details because we are also using this to teach here the same article to master students as a very basic introduction, because the master students who come here, they are from various backgrounds, sometimes even from economics. So we don't want to give them like a more descriptive article as a starting point. So yes, the article that I mentioned does contain math details and how you can work out the probabilities. But you are right, there are much more advanced articles and much more details if one wants to kind of look at it.
Thank you, Professor K.S. Mallesh sir, for joining and asking this question. If any other questions, we will take it. Please raise your virtual hand or type in the chat box. Are there any more questions? If not, we will wind the. Yes, yes, ma'am.
Just sir, one more thing. I think Dr. Raghavendra Krishna has shared his email ID. I would just like to know, does he require some article? Or oh, okay, he has asked me to share his email ID. Okay, fine. I get it, sir. Thank you, sir. Yes.
Okay, okay, ma'am. So thank you very much, ma'am. For engineers, it may be difficult, really, since
Okay.
I'm also an engineer. Uh, but for this, we have been requested, madam, for PU students in the physics stream, we wanted to have this subject. So that's why madam has given this quantum subject as a today's session. And the career options also, career opportunities for them if they take it in their future as a education. That's why we have requested, and he has delivered very well in this domain. Thank you very much, ma'am, on behalf of all the teaching faculty and all the students who have joined with us. And today, due to some technical errors, we are lost in between the connections, and there is only 50% of the session has been live streamed. Later, we will be share it once again, the recorded stream. So sorry for the inconvenience caused due to some network issues. And thank you, madam, once again from KSTA and on behalf of all the teachers present here and students who have joined with us in YouTube channel later. And thank you all the students for joining with us. Tomorrow, I request all of you to join. It's related to time management for the students. Thank you. Thank you very much once again. Today we will end this session.
Thank you, sir.
Thank you.
Thank you.
Thank you, madam.